So in this lab, we will be determining the rate of a reaction, and we will be using a specific method called the initial rate method, which I'll talk about soon. And we are looking at potassium permanganate reacting with oxalic acid. So we're starting off with just some basics about rates in chemical kinetics. So the different types of rates that you can measure for a chemical reaction are instantaneous, average, and initial. So each of these means something different, or they can be measured at different time points. So for initial rate, it is measured from the very beginning. So you see how this arrow is pointing to that rate right there, and it is starting, or it's measured from point zero, time point zero. So as soon as the reaction starts, the timer goes off, and then you watch the reaction happen, and you basically measure that rate. Now, this isn't for the entire reaction overall, right? But this does give a lot of information overall. That's initial, and you'll see right now what type of information we can calculate. But as for the other two, so instantaneous is at any other point in time. So it's similar to initial, and it's better for me to say actually initial is an instantaneous rate that is measured, but it is specifically at time point zero. Instantaneous can be at any time point, but it's also at one instant. It just happens to be at a different one in comparison. And then finally, the average is what it sounds like. The average rate is just over a certain period of time. So it would be, the average between time point 0 to time point 24 hours, right? The initial rate measurement is useful in determining the overall rate order of a reaction. So that's what we're going to be working with here, the initial rates. And this method is commonly used in order to determine these rate orders overall. So what is this initial rate method that I keep mentioning? So these are pretty much the guidelines that you would use to complete this method and determine the overall orders that you're looking for. So the order with respect to a particular reactant can be determined by varying its initial concentration while holding other concentrations constant. So major idea about this method is that one reactant concentration will be changing, the other reactant should be staying constant, so that whatever change that is occurring to the rate is because of the one that you're varying, okay? And we'll see right now in an example what I'm talking about. So these rates have to experimentally be measured. You can't just calculate them with some sort of computer, some sort of program. They have to be done in the lab, and you're literally measuring the rates. The change in rate is a direct result of the reactant. So that's the whole main idea, is that, or that's what you should be looking for anytime you're doing the initial rate method, is looking for when one of your reactants, the one that's changing, how it's affecting the rate. And then from there you can calculate the order from the change in rate because of that one reactant. And you do the same thing to the other reactant while holding the other one constant. And you repeat this with all reactants. So here I have an example. Now this example I have already done in a pre-recorded video. So because of that, I'm going to let you watch that video for an example. And the reason I'm mentioning this is because in, for example, lab 3, where you did the molar mass freezing point depression, I did the example at the end of that same video, but that was because I didn't have a strong example, or just an example period, in the pre-recorded videos, the lecture videos. So here I already have this specific example filmed, and I have the link to the video in the lab handout, so you just have to click that. So I won't be going through it specifically, in detail, but I do want to point things out to you that will help you kind of get acquainted with the lab you're about to do. So this is an example where you would determine a rate law from initial rate. So we are completing the initial rate method in this particular example. So notice what you're given right off the bat, this table with a bunch of data. Notice that This is obviously relevant to this chemical reaction, right? We have NO reacting with ozone, with O3, and then you're getting some products from that, okay? That's not really the important part. The important part is noticing what data you have and for what, parts of this reaction. So the data you have is this right here for NO and for O3. Now, what is this thing in the brackets? Anytime you have brackets in this class, in Chem 2, that means concentration, okay? Or molarity. Those are synonyms for each other. Now, why are they synonyms? Remember in this previous chapter about colligative properties where we learned about different concentration units? Molarity is one of those concentration units. So if we say concentration, we can that can be synonymous for molarity if that happens to be the unit that we're working with, okay? And these brackets typically mean molarity. So here we are looking at, in terms of this data that we're given, we're looking at molarities of NO right here, right? And for O3, we are looking at molarities. And now we have 5 different trials with a bunch of different molarities for both NO and O3 that you are reacting. And then finally, in this column, we have the rate. I know this isn't, written out, but as part of this chapter that you're studying on kinetics, you should understand that anytime you have a concentration, so the brackets, divided by time, that is a rate, essentially. So, overall, what do you have? You have 5 different trials, I was going to say 6, 5 different trials of NO, you have the concentrations of both the reactant NO and then for the O3 reactant. So you have information on the reactants and then you have the reaction rate overall, the initial reaction rate overall. So what you're going to do for this lab or for any initial rate method example problem that you have to do, you always start off with one at a time. So let's say we wanted to determine the overall order, because that's your main goal, is to determine the order of everything that you're working with. So you would have to understand that the rate is equal to, the concentrations of your reactants times a constant, okay? So here we don't know our orders, but that's important for the overall rate law, right? You can't determine the rate law without that. So for the initial rate method, understanding everything I just went through is very important. So hopefully after you get through that, then you can begin to apply everything. So your first step, if let's say we were determining the order for NO, right? We're going to focus on NO. You would look for where NO is changing, the concentration of NO is changing, but the concentration of O3 is staying constant. So for example, and you can pretty much spot it, pretty quickly once you kind of get familiar with these problems. So in trial 3 and 4, NO is essentially doubling, right? It's going from 1 times 10 to the negative 6 to 2 times 10 to the negative 6. It's doubling. But O3 is staying constant. It stays the same, 9 times 10 to the negative 6. And the rates are changing. So because we know that NO is changing, the concentration is doubling, and then something is happening, it doesn't matter really what. We're not actually looking at the numbers right now. I'm just trying to kind of train your eyes to looking at this, right? The rate is changing, so we can attribute that change to the fact that the concentration of NO is changing. And because O3 is staying constant, we can say, okay, we know that change in rate right there is because of NO and not O3. And then from there, you just set everything up, you divide some things out, and I'll let you go through that example in that pre-recorded video. I also posted the link for a Khan Academy version of this same type of problem. That video is also great. Whichever one helps you learn better. I know sometimes I may not be as thorough as everybody might need, so that's why I like to give sometimes other options. So check those out. for the steps on how to actually calculate this out. This was more just like kind of getting your brain primed for working these problems out, all right? Okay, so now that you have all that background info and you're a little bit more prepped on how to approach all of this information in this lab, this is the procedure. So you're going to do the routine stuff, research the MSDS for the reagents that we're using in this experiment. You're going to fill it in the table. Calculate the average times of reaction in part 3, data collection. So that's going to be the first thing that you actually calculate in the next part in your applied exercises. But it's present, all that data is present in part 3. So you'll see right now, I have pictures of it. And then finally, we'll use all of that to apply and complete the initial rate method. Okay, so now we're at the data part. This is the fun part for me. I know you're probably rolling your eyes and you're like, oh, I hate this. It's okay. So you're given a good amount of tables, and they might look overwhelming at first, but I'm gonna kind of break down exactly what each of these tables are giving you. So, table 2, experiment preparation data. All this is giving you is the volumes of the amounts of our reactants that we are reacting, right? So for example, for all the trials in experiment 1, we have we're mixing 2.5 ml with 0.5 ml of potassium permanganate, and we're also adding in a few ml of water, 3. So each of these just has a specific, like, it's like a little recipe, right? And each experiment has its own little recipe. And this is important later on for when we're calculating something in the applied exercises. So keep this in mind, that that's all it is. If we were doing this in person, these are the like volumes that you would actually be mixing in test tubes, as you can see here. Like this is how your test tubes would look like. So imagine that you would be mixing those amounts, okay? Now, so yeah, we prepared these test tubes in the experiment. So what this is a screenshot of your lab handout. So if you want to follow along, if you have that printed out or anything, you can, underline stuff, highlight stuff, whatever it is you need. So a stopwatch was used to time the reaction after all 3 solutions were mixed together. The following data in tables 3.5 was collected at room temperature 25 degrees C. So tables 3 through 5, that is showing you the reaction time data. So what this is the amount of time it took for the reaction to be complete. So by complete, we mean that for this particular reaction, you'll see a color change. It starts off purple, and you can see it there, and it turns into this like dingy yellow, basically. And these screenshots right here are from a YouTube video. I linked this video in your lab handout in the objective, the introduction part. So you can take a look if you actually want to see this reaction happening. If we were in lab, you would be seeing it. But this is the next best thing. So what are these tables showing you? We happen to have more than one trial for each type of experiment we're doing, okay? So that's why here we have 4 different times that we measured for experiment 1. So the reason that this block right here is like blank is because it's the same volumes throughout, okay? So that stays consistent. It's just, we didn't type it out. Remember, chemists are lazy. We don't type things out if we don't write things out if we don't need to. So 4 trials, that's what you see here for experiment 1. And then same idea for experiment 2, you have 4 trials. These were the times for them to be complete. And then experiment 3, 4 trials, the times for the reactions to be complete. That was your data. Now what are you going to do with all this data? So I have it listed out step by step, similar to your previous lab on the molar mass freezing point depression. And for most labs, I will kind of, list it out for you the steps that you need to do, just because it can be confusing. You know, we're not in person where I can kind of say it to you, you know, face to face, and it's just like easier to kind of, with the entire class, make things very clear. So instead, I kind of just have to make it clear right there on the handout. So just expect those. You don't have to worry about like me just throwing a handout at you with no explanation on the calculations. And I try to relate it to lecture as much as possible. Okay, so yeah, step by step, first you're going to find the average time of reaction. So that's going to use those 4 different trials, the times for each experiment. You're going to use those 4 values, you're going to average them out, and you're going to report it into table 6. Then you're going to calculate the concentration of both oxalic acid and potassium permanganate for each experiment using the dilution equation. That is this equation right here. And I'm giving you a major hint on exactly what you're solving for. So first you manipulate the equation to solve for M2. Then you're going to plug everything in. I will leave the volumes up to you. So remember that in table 2, I give you volume. So I give you the little recipes for each reaction for each experiment, right? Notice that there will be a total volume. I didn't give you the total volume, but I think you can calculate that, and I'll leave that up to you. So the initial concentration for oxalic acid is 0.755. The initial for potassium permanganate is 0.13. So make sure to use those and use the correct one for whichever concentration you're calculating. Since we are mixing 2 reactants, the volume is combining, okay? So that's what I just mentioned right now. Keep in mind that you're mixing oxalic acid, the volume of oxalic acid, the volume of potassium permanganate, and also that water that we needed for the reaction. So keep that in mind when you are, you know, determining your volumes here. And you will end up having a lower concentration, okay? You're going to report this in table 6. And then we will calculate the reaction rate by dividing the concentrations that you determine for KMnO4 by the average time of reaction for each experiment, okay? And it's as simple as it sounds. You take the molarity that you calculated for, you know, for example, experiment 1, you divide by the time, the average time of that reaction, and then you report that in table 6. Here's that actual table that I keep referencing. So first, and you kind of go in order. So first, the average time of the reaction is that we calculate. Next, it's those concentrations. So that's whenever you use the M1, the dilution equation. And then finally, you take the concentration. So in other words, you're going to be taking these right here and dividing them by these up here. And you report that right here. And then, sorry, you're not done. You will use all that information to determine the initial rate method, okay? So something to note is I have the table set up a little bit differently. So I have it set up where the experiments are up here, and then the reaction rates are down here. So remember earlier we had the reaction rates over there on the right-hand side, and then we had the concentrations going the other way. So just keep that in mind, right? The concentrations were right here. Keep that in mind whenever you're looking at which ones stay constant and which ones change, okay? And then, okay, so you're gonna watch that video on its own, because that's its own, you know, process. And it's something you practice in lecture as well. So hopefully if you practiced it already, you're kind of familiar with it. But after that, you're gonna report all your values here. And, you know, same as always, if you have any questions, just let me know and I can assist you.